Welcome. Hey team, it's fun to see some familiar names pop up. Even though your screens are black, I really appreciate you coming back. Hey Missy, good to see you. Thanks so much for coming out tonight or whatever time it is where you're at.
East Coast. Nice to see you,
East
John.
Coast. Yeah, great to see you too. I'm on the East Coast as well.
Oh, okay.
Here in a basement in central Vermont.
Oh, it sounds much better than my basement here in New Jersey.
We've got what do we got? Some New Jersey. Yeah, if folks wouldn't mind popping in the chat where they're coming from. Yeah, I work for those of you that are popping on here. We'll give some folks a minute, some other folks to join. But my name's John Griffith, and I'm a curriculum developer for an organization with the longest name possible. If I could just call it Series CEEE, that would be good, but no one would know what that means. So I work for an organization at the University of Colorado Boulder called the Cooperative Institute for Research and Environmental Sciences. That's the series part for the Center for Education Engagement and Evaluation. So Series CEEE, more or less, my job is to be a liaison between the earth scientists that I work with at CU Boulder and NOAA to bring their contemporary earth science research into classrooms by developing resources. So I'm a former eighth grade science teacher. I spent about 15 years in Flagstaff, Arizona, before I've since moved back to Vermont and have a couple kids and family nearby. But tonight's topic, water in the West, near and dear to my heart, having spent so much time. NAU, that's right. I'm an NAU grad as well, Emily. I'm not sure if we figured that out. Yeah, I got my master's in geology out there and then in science teaching and taught out there and spent a lot of time on the Colorado Plateau. And so, wow, that's the longest, most random introduction I've ever given, but that's a little bit about me um, and I'm psyched to dive in tonight into a new type of webinar that I've been offering this fall. New to some of you, old to those of you that have been here the last few weeks. But excited to highlight a new data sense making strategy that we've integrated into a data puzzle lesson called what's it called? Megadrought in the Colorado River Basin. And so for those of you that are new to data puzzles are instructional lessons that are about 180 minutes that combine classroom-friendly data sets with ambitious science teaching practices to support students in making sense of phenomena. And we'll talk a little bit about the instructional framework here in just a moment, but all lessons follow the same instructional framework that I was fortunate to get to develop with co-author of Ambitious Science Teaching, Melissa Bratton. And so tonight we're going to engage with this instructional framework in the context of the Megadrought and the Colorado River Basin lesson. And we're going to try out a new strategy that we've just added to that lesson called the zoom in strategy. And so part of this webinar series is designed to highlight some new strategies that we've added to data puzzle lessons to support students in making sense of the data sets. And so tonight we'll talk about the instructional framework. I'll put some context around the data set that we'll look at together. And then we'll see how time is. We'll either talk through the zoom in strategy or engage with that zoom in strategy a little bit together. There won't be breakout rooms, so even though I say we're doing it together, those of you who are scared of breakout rooms or don't want to do that tonight, don't jump off the call. We won't go to breakout rooms, but for folks that are interested in maybe using the annotate feature or popping off and showing their faces and speaking, there will be opportunities for that, but no pressure this evening. So I'll be presenting for the first 30 minutes tonight, and then our colleague Seth Arens, shown down here in the bottom right corner. He's a hydrologist and ecologist with the Western Water and Assessment. He lives out in Salt Lake City, Utah. He does a lot of work helping communities in the Western United States deal with water issues, not only drought, but also flood. He was just working with a community in southwestern Colorado who recently experienced some pretty significant flooding. That's in Pagosa Springs. But he's going to talk about his work, water issues in the West, and in particular, he's done some really interesting work in Glen Canyon. So Lake Powell is one of the largest reservoirs in the United States. It's northern Arizona, southern Utah borders those two states. And the side canyons there that had been flooded by that reservoir as the water level decreases in Lake Powell, those canyons are now being exposed at the surface, and he's studying the different vegetation types and the different communities that are emerging due to the mega drought. So he'll talk about the state of the mega drought, but also some of the research he's doing around the things that are coming back in these exposed landscapes. So that's the scoop this evening. And while I gave you that long-winded introduction for myself, tonight I'm just this talking head for a hugely collaborative team, only noting a fraction of the names here that have contributed to this work. I mentioned earlier Dr. Melissa Bratton at CU Boulder, a co-author of Ambitious Science Teaching that helped develop this framework. Ceres has about 800 earth scientists within its organization, and so I've been fortunate to get to work with many of those earth scientists to translate their research into classrooms through the development of resources like data puzzle lessons. Big shout out to Kristen Hunter Thompson and Annette Brickley of DataSpire. They do so much good work with science and social studies and math teachers across the country, working with teachers and then students to better prepare them to make sense of data in their classrooms. Dr. Jessica Peen at UC Berkeley, really important in terms of the climate understanding side of things, and how do we think about coherently integrating data puzzle lessons into classrooms. And then we've worked with 500 or more teachers like yourself over the years, facilitating webinars, running PD, piloting lessons, presenting at workshops, writing papers that have been published in NSTA journals. We couldn't do this without you all. In fact, it's my favorite part of the job. I often say this, writing curriculum in my basement is not my favorite part of the job. It's getting to connect with teachers and students and bring this research out into the world. That's the best part of this work. So thanks for being here. And special shout out to this group of middle school science teachers in the bottom right corner here. These are 19 middle school science teachers from the Colorado Front Range that came to CU Boulder last June for a 3-day PL professional learning experience focused on some of these new strategies and data sense making practices that I'll be introducing tonight. And so these teachers are actively using data puzzle lessons that have these strategies and giving us feedback on how they go with these individual lessons. So we're in classrooms filming, documenting what teachers and students are doing, and all of that is going into these lessons and these teacher guides to create as strong a product as we possibly can for everyone. The data puzzles instructional framework. Forgive me for those of you that have already seen this before, but I think it's important for those of you that haven't to understand that all data puzzle lessons follow this structure. They all start with this practice of eliciting students' ideas, where students are presented with an opening scenario. The scenario is something that they might be familiar with. In this case, on the context of the mega drought lesson, we just asked them, have they ever experienced a drought for themselves or heard about a drought? What does that look like? Or what might be the impacts be of that? Eliciting students' ideas about a drought or albedo in the context of like, have you ever been outside on a snowy day and it's super bright, it hurts your eyes? Or have you ever walked on pavement in the summer barefoot? Like, how does that feel? So experiences that students may have had, revealing those experiences, revealing their language and ideas about what it is and why that happened to them, and then connect that opening scenario, those student experiences, to something that has similar science content in a new phenomena, in a new scenario, a science investigation that a featured scientist is undertaking. And so what that might mean, right, if we're talking about drought and student experiences with drought, I would then maybe in part two, identifying important science ideas, introduce Seth Arens through an interactive reading, a hydrologist and ecologist who studies drought on a larger scale, drought that happens over decades, these mega droughts. We have students construct some initial models about an investigative question and make predictions about that question. And then this is where a lot of the work over the last year or so has come in this third quadrant here, supporting ongoing changes is in thinking, where we're integrating new strategies. Again, that's what we're working with that cohort of Colorado Front Range teachers to do, integrating new strategies to support students analyze and interpret data in the context of the investigative questions. We have scaffolded prompts to support them in revising their predictions, and then they're asked to put the pieces of the puzzle together, so to speak, to construct a final model representing that investigative question. So these are the kind of nuts and bolts of it. Each lesson follows this framework. There are some nuances and different strategies that we've used for each lesson. But again, yeah, what you see here is what you get in those lessons. Data sense making is this buzzword we're throwing around, and we want to define it for folks this evening and moving forward. When we're talking about data sense making in the context of our data puzzle resources, we're talking about the exploration, analysis, and interpretation completed to investigate science phenomena. And so Kristen Hunter Thompson and Annette Brickley, who I mentioned earlier, have spent much of the last year thinking about what practices are needed in order to support students' sense making of data. And where they started was they looked at the science and engineering practices and started to pull them apart into practices that are more specific to this data sense making. They were thinking about, how do we set students up? If we're analyzing and interpreting data, what does that mean? How do we set students up for success when we're analyzing and interpreting? And so from this kind of pulling apart of SEPs, this is just a small fraction of some of the work that we've done, but wanted to illustrate it for you here. Pulled apart the SEPs and tried to define them, describe them in ways that were more connected to this data sense making. And so analyzing and interpreting data, what does that mean for us? Data puzzles, that means we're asking students to describe visual patterns and then interpret those patterns in context. But to support teachers and students in enacting these practices, we are including strategies to build student skills around these practices. And so tonight, well, we'll talk about what that looks like here in the schematic some of you have seen before. A lot of our data puzzle lessons start with trying to build student skill around describing visual patterns. It's a real central sense-making practice. And if we want students to describe visual patterns, we might select a certain strategy that supports them in making sense of whatever data set that we are integrating into a lesson. And so tonight we'll engage with the zoom in strategy. And for the zoom in strategy, we're going to focus on different parts of a data set, different parts of a graph at different times, at different scales. And while we're doing that, or while your students are doing that, so you're enacting this strategy, and the strategy necessitates students to take a certain action. Maybe that's they're annotating a graph or annotating portions of a graph. Sometimes that's highlighting different features. Sometimes it's just some certain talk moves that are integrated into lessons, but students are always taking some action in response to the strategy that you facilitated for them or a teacher has facilitated for them. And that action that students take is designed to support them in building that sense-making practice, building that skill, in this case, describing visual patterns. So Again, we've integrated different strategies to support students doing certain things, taking certain actions with the data set to build a skill here. And so again, tonight, we're going to engage with that zoom in strategy in the context of this particular lesson. I haven't looked at the chat in a long time. We got some lumberjacks here. I like it. Couple lumberjacks. I feel at home. Great. So yeah, with regards to this lesson, again, not shown here, that eliciting of students' ideas, right? We might introduce drought to students, talk about what drought means to them, where they've experienced that in their lives. And then we distribute this interactive text, this puzzle plot text that has different videos, graphics. Teachers often choose to read these aloud with a class so they can pause to talk about different parts of the text or different images, watch some of the visuals together. Um, we won't read that tonight, but I wanted to call out some of the main points from that text. The puzzle plot text describes drought as the difference between the water gained through precipitation and the water lost through evapotranspiration. This is a picture I took years ago with students of mine on the Colorado River when I was a middle school science teacher out in Flagstaff, Arizona. Um, and so in this particular, the balance between water coming in and water going out, evapotranspiration, the loss of water through plants and directly from water sources. Something we call out in the text is that with warmer temperatures, more water is lost via evapotranspiration. So temperatures play an important role in drought because warmer temperatures, higher rates of evapotranspiration. So many of us, most of us have experienced drought. A mega drought is a period of extreme dryness that lasts for decades. In this Colorado River Basin, down here outlined in blue, is a region where 40 million people live and has been experiencing a mega drought since the year 2000. So more than 24 years of droughts. And through this puzzle plot, we've kind of contextualized a question. And the question in this lesson is what factors are contributing to the mega drought in the Colorado River Basin? So we've tried to kind of plant a couple seeds by talking about precipitation, evapotranspiration, and temperature. Get students thinking about those factors and framing it in such a way that those factors we hope will come up when students are making a prediction about this question. After students kind of summarize big ideas from that interactive text, have made a prediction about that question, what factors are contributing to the mega drought in the Colorado River Basin, we then have them look at temperature and precipitation data set collected from weather stations across the Colorado River Basin to compare temperature and precipitation amounts. Again, in the context of the mega drought, something changing with temperature and precipitation, like could one or both of those factors be contributing to the mega drought? And this is where the zoom in strategy comes into play. And so with the zoom in strategy, what we'll do here this evening is we have about 125-year record of temperature and precipitation from the Colorado River Basin. And rather than give students or give you all that entire 125-year record, we'll break it up into portions. You could 50-year increments, 25-year increments, whatever it is that you see fit for your students. We prompt students to look at portions of the graph at different scales, at different times, and they consider what they see and what they can say from the data. We require that students annotate these portions of the graph that they're looking at. So they need to be printed for students, or there needs to be a way for students to annotate them in a slide deck or some way to do that. And it helps bring focus to patterns at different parts of the data set and helps students build meaning as they learn more information. So they might look at one portion first, then another portion, then another portion. So hopefully different patterns emerge. Students may have a better chance to look at some of the variability we want to talk about variability in data sets. And by focusing on different parts, we might see some of this variability. Maybe it's less scary. And this strategy encourages flexible thinking, right? As you're looking at one portion, your thinking might need to be revised as you look at the next portion. And so again, you set it up by using different scales, different maps, space, time, right? Lots of opportunities to kind of chunk it for students. For the data puzzle lesson, here's the 125-year record that you would not show your students initially. This is not how it's presented in the actual resource. But you'd facilitate it like a jigsaw. At least that's the way it's written in this lesson, where student pairs are assigned a variable, temperature or precipitation, and maybe this student pair gets temperature, and they might get these three graphs or portions of temperature data set from these three time periods. Another student pair might get these same time periods for precipitation, and they're asked to annotate, draw on each of these portions to highlight what they see, what they could say, things they're wondering maybe. And after, it would be the teacher's job to facilitate a whole group discussion about the annotations that different pairs and different groups made. And the way we've seen this done really well is by focusing on maybe you yourself as the teacher have these different portions printed and you tape it onto the wall and you annotate based on what the whole class is saying. And then you can tape the next time period up and the next time period up after that. And so you've got this chronological temperature graph that you've built with your students. You've got the different patterns and different things that popped out to students across these different portions. And so again, you can look at these patterns and portions and then build patterns over the entire record in that way. Um, let's try this out. You've got enough people have commented in the chat where I feel like people are still here. And what I'm going to ask you to do is in the bottom left corner, there's of your screen, if you kind of move your cursor, there's a little pencil that shows up in green. We've done this last week, so I know some of you that were here know where this little green icon is. And then if you could annotate this graph to just highlight what you're seeing, things that jump out to you. We've got a temperature record from the Colorado River Basin from the year 1900 to 1949. For those of you that don't want to use the annotate tool, maybe you could use the chat. Oh, we've got Emily and Jessica in there. Awesome. So we've got some people circling some things. If you don't want to annotate, maybe you could add something in the chat, something that stands out to you. And again, the way you would do this with your students, like a student pairs or a group, you would actually print this out, this graph, give it to them to do what it is that you're doing here, or they could describe what they're seeing, much like you're doing. Great. So some of the things that are jumping out to me, people have circled some of the high points. So somebody circled the units here as well. So we're looking at a temperature record in degrees Fahrenheit, ranging from 48 to 55. We've got some different high points, high temperatures. We can say when those happen, some low points. I see a line here kind of describing the overall trend. Cool. If I look at maybe, if you were to look at maybe the average temperature over this time period, maybe around 51, right? So kind of a different way to explore one time period. Let's see, I'm going to clear this. Maybe we'll take a mental snapshot here. Clear all the drawings. I'm going to go to the next, well, I'm going to go to the next slide, 1950 to 1999, and ask you to do this same thing. So again, lean on folks that were already in there. We'll do some more annotating. Again, this is what you would do with your students after they've got, okay, we've got a line starting around 1975. So people are circling something's going on. Got a high point in the early 80s. So again, it's the same temperature scale, right? This is what allows you after the fact to kind of take these up on a board and build this record chronologically. Got some interesting low points here in the late 90s, people are pointing out. This big circle here, not much change around 1970, something in the mid 70s, we start to see this increase. Cool. Maybe if I said what the average temperature would be here, I might say the average temperature during this time period is closer to 52. Remember back, it was maybe closer to 51 in the previous 50-year time period. I'll clear drawings here. We'll do this one more time. 2000 to 2049. We don't have observational data beyond 2025, beyond this year. So this data set goes up to 2024. If you could add a few annotations here, if folks, maybe we had people in the past, if they want to project out into the future, we had some people start to do that. We got somebody, I don't know if that's maybe a best fit line or average closer to 53. Someone's got this projection out into the future. Looks like they're increasing, but you might not know, you might not make this line unless you'd seen the previous 100 years of data, highs and low points. So lots of different things are jumping out to you is kind of the point of all this, and we hope that's the case for students. Lots of things can kind of jump out to you as you're looking at this graph, this data set in these different subsets, these different portions. I'll clear these drawings now. Thanks so much for going through that exercise with me. And after that is when you might build that via a whole class discussion. Look at the first 50 years, second 50 years, last 25, 50 years. And you can see that this temperature graph, this temperature data set, this is from a previous PL, some of these different trend lines, but mostly flat. We don't see that increase really start to take shape until the mid 1970s, where we see temperatures, really this increasing trend start to take off. You can see temperatures in the previous, I mean, from 1900 to 1950, maybe an average below 51. The next 50 years, 1950 to 2000, that average increase. And then last 20 years, the average significantly higher, perhaps around 53 degrees. So we see these different trends, these different high points, low points, lots to kind of make sense of here, lots of things to talk about with students in terms of variability, trends, high points, low points. We ask students to then a different group might do the same thing in the context of the Colorado River precipitation record. And so again, 50-year increments, looking at high points, low points, ranges, trends, all of these different things, lots of opportunities for rich discussion. This slide's pretty brutal. I'm sorry. But basically, after you're facilitating that zoom in strategy with your students, facilitate this whole class discussion, you've described some visual patterns. It's time for them to kind of describe those patterns for themselves, interpret those patterns in the context of this investigative question here, the factors contributing to the megadrought in the Colorado River Basin. And students have these graphs in full on a worksheet where they're asked to look for the highs, the lows, to calculate an average, perhaps collectively as a class using this spreadsheet that has the entire data set. We have teachers, I have these lines here. We have a lot of times teachers will ask students to add a line right at this year 2000, since the puzzle plot text defines the year 2000 and thereafter as the period of megadrought. So again, we're looking at factors contributing to the megadrought. So what's changed post 2000? And so from these scaffolded questions about these graphs, after that, we ask students to construct a final model, a visual representation of how things, maybe conditions have changed past to present. We might see a model that looks something like this, where in the past, the thermometer may be drawn in a little bit less, cooler temperatures. The present, you can see this lesson's been around for a few years. The thermometer is up a little bit higher, warmer temperatures. With warmer temperatures, we expect to see higher rates of evapotranspiration, water loss. So those red arrows are a little bit longer here. Maybe the blue arrows, precipitation a little bit shorter here. So opportunities to visually display some of the patterns that we saw in the data set. So if we were to put all of this in context, again, this is a whirlwind, a lot thrown at you, but putting the Megadrought lesson in context of this instructional framework, there's some eliciting of ideas at the beginning, asking students about drought, what they've heard, how they've experienced, maybe use their ideas, their experiences, their language to introduce this investigative question, the factors that are contributing to a megadrought, a decades-long drought in the Colorado River Basin. Um, Students make a prediction about this question and then would engage with that zoom in strategy before to describe visual patterns in the data set before interpreting those patterns in context via some scaffolded prompts. And then they construct a final model. So again, we're looking at what we think is around 180-minute lesson. There's slide decks, student worksheets, answer keys. We're continuing to update the teacher guides based on our classroom visits this school year, but we hope that we're confident that this is a resource that's being used quite widely, and excited to work with you tonight and in the future should you be interested in this, but have questions, always feel free to reach out to me, and I'll make sure you have that email at the end. Emily has a question. Do they construct an initial model? Yes, Emily, they do construct an initial model. I'll in the chat just in just a moment put the student worksheet into the chat, and you'll see the initial model kind of comes after the puzzle plot text. We have them practice making an annotated sketch. Yeah, great. Thanks for that question. Seth, I went a minute over. Thanks so much for being here. Seth Arens, an ecologist and hydrologist. He's trying to figure out what's contributing to the mega drought in the Colorado River Basin, but perhaps more what he's doing is exploring the impact of the mega drought on living things. Seth spends a lot of his time in Glen Canyon, the various canyons that surround Lake Powell, again, investigating successional patterns as the landscape emerges, as water level declines from the drought and the landscape emerges. But Seth and I were also talking most recently about some of his work working with Pagosa Springs and communities that are impacted by flood. So drought, floods, lots of things going on in the Western United States. And Seth is here to kind of talk a little bit about his work, provides an overview of the current state of the mega drought, and then perhaps selfishly, what I'm most excited about, Seth, is what's going on in Glen Canyon with your research. So Seth, thanks so much for being here.
You're welcome. Thanks for the introduction, John. Let me just share my presentation here. Do I need to switch displays, or are you seeing the?
No, it looks good. It's refreshing to see some pretty pictures, Seth.
Oh yeah, lots of pretty pictures in this presentation. So my name's Seth Arens. And I'm going to talk more about impacts of the mega drought rather than the drought itself. I will give a little context and background as to kind of following up a little bit on what John was just talking about on how we've gotten to this point of drought in the region. But mostly I'll be talking about what's happening. So one of the consequences of Lake Powell of the mega drought is that the large reservoirs in the Colorado River Basin are very low. And what I'm interested in is, well, what's happening on the land surface that used to be underwater in Lake Powell, but now is a landscape? What sort of plants and ecosystems are establishing on that? So Lake Powell is drying rapidly. This is an image of Lake Powell around Bullfrog Bay, which is a common access point to Lake Powell when the reservoir was not totally full, but nearly full. Um, and in the last time the reservoir, this image is from the 80s, but the last time the reservoir was almost full, just 3 feet away from being full, was in 1998. But we've seen a 150-foot drop since 1998. Now the reservoir sits 150 feet lower at 3,545 feet at 29% full. And you can see by these two satellite images that the area covered by the lake as it is at a high stand versus a very low stand is tremendously different. So there's a massive amount of land that used to be underwater, but is now a terrestrial landscape. But how have we gotten there? How have we gotten to that point of Lake Powell? Why has it dried so much and so rapidly? And why do we even care about this? Well, as you were just discussing, but I'll add a few other points to that. Lake Powell is so low, and there's a lot of other impacts of the mega drought within the Colorado River Basin, but Lake Powell is a nice integrator, kind of a time integration of how the drought is impacting the region over a long period of time because it's such a large reservoir. It stores about 2.5 times the annual flow of the Colorado River. So we're seeing Lake Powell being so low because not just because of one thing, but really a combination of three factors. Water use, how we use water in the West, drought, and climate change. And I specifically bring up increasing water use since 1922. And I bring up that date because that's the date that the Colorado River Compact was signed. That is the governing water policy that determines how the water in the Colorado Basin is split up. And how that was split up is the basin was divided into really three components. The upper basin, so the upper basin states are Utah, Colorado, Wyoming, Utah and New Mexico. The lower basin states are Arizona, California, Nevada, and also Mexico. Um, and the reality is that the size of the size of the water that was divided up in the 1920s is more water than we have available in the river now. So the kinds of things that you were just talking about with increasing temperatures causing decreasing flows in the Colorado River, well, these things are playing out by there's simply just not enough water anymore. While we haven't like quote run out of water, that's really only because we have these two large reservoirs in the Colorado River system, Lake Powell and Lake Mead. Together, they store approximately 5 times the annual flow of the Colorado River. So essentially, you can think of that as a bank account. And during this mega drought since the late 90s or 2000, we've been drawing down that bank account. So we've still been using the amount of water that everybody's supposed to use. However, there hasn't been enough flow coming into the reservoirs to keep them full enough. So now I want to take a different look at sort of these how Colorado River flows have declined over time. So I'm not going to bore you with many graphs. This is one of the few graphs I'm going to show. This shows annual water supply in the Colorado River Basin. And the units that we use for that are millions of acre feet of water. Acre feet's kind of a strange unit of measurement. What an acre foot is imagine an acre of land, so a piece of land about the size of a soccer field, fill that with 1 foot of water. That is 1 acre foot. So this is showing the variation in annual water supply in the entire Colorado River Basin from 1905 to 2021. And this black line that I put up there, that's how much total water is allocated in the Colorado River Basin. This is 16.5 million acre feet. That's not necessarily how much is used. We don't use that much water, but that's how much water is out there in terms of water rights. The lower basin uses all of their water rights. The upper basin uses about 2/3 of their water rights, and Mexico uses all of theirs. So in the 1920s, they didn't have this long historical record like we did. we do now. They had data from 1905 to 1922, and the average flow from those years preceding the Colorado River Compact was 18 million acre feet. And they thought, oh, well, if we set this at 16.5 million acre feet, then we've still got 1.5 million acre feet to play with. At the time, they probably only used about 4 million acre feet in the entire Colorado River Basin. So it probably seemed like somewhat of an endless resource. However, if you look at the long-term average of this whole record, it's significantly lower at 14.6 million acre feet, and that's significantly lower than what's allocated within the basin. And now I'm going to kind of look at these 30-year time periods, starting in 1970 to illustrate decreasing flow in the Colorado River. From 70 to 2000, you had about 15 million acre feet. By 1981 to 2010, this declined to about the long-term average. If you look at the last 30 years, ending in 2022, only 13 million acre feet was the average for the basin. However, if you look at this mega drought period, starting in the year 2000, the average flow is only 12 million acre feet. And remember, that black line is how much water theoretically could be used in the basin. So there's a mismatch there in the math by about 4 million acre feet. Now, this green line is average temperature in the Colorado River Basin. You were just looking at these data, and it shows similarly what you saw, a really dramatic increase since especially 1980, and there's been a 2-degree temperature increase since 1950. And it's really this increasing temperature, not a change in precipitation, that's driving a long-term and progressive decline in water supply in the Colorado River Basin. And this is uh, largely being forced by warming temperatures, but superimposed on that is also the fact that we've been in this drought period for the last 20 to 25 years. So the combination of those two things are really, and then how much water we use in the basin is really driving this dramatic decrease in Lake Powell elevations. And I want to stress that this decrease in water supply in Lake Powell is not caused by a single thing. It's not just caused by mega drought. It's caused by the combination of how much water we use, drought, and the impacts of climate change. And while this is really important with thinking about water supply for the 40 million people the Colorado River supplies, the 6 million acres of land, of farmland that's irrigated by Colorado River water, what I'm most interested in is what's happening on all this land that used to be underwater, but it now is a terrestrial landscape. And in fact, when the lake hit its low point in 2023, just before runoff from that year hit, there was over 100,000 acres of land that was previously underwater that now is a terrestrial landscape, and ecological succession was occurring. So I want to give just a little bit of a summary of uh, the landscape that was flooded by the construction of Glen Canyon Dam in 1963. It took about 20 years for the reservoir to fill, but when it did fill, it flooded 185 miles of the Colorado, 18 miles of the Dirty Devil River, 28 miles of the Escalante, and almost 70 miles of the San Juan River. There are 127 named tributaries that were partially flooded with the filling of Lake Powell. While there's major rivers that come into the region, including the Colorado, there's all these smaller tributaries that carve canyons through the Colorado Plateau and down to the Colorado River. And by April 23, it was in fact 103,000 acres of land that had emerged from Lake Powell. At current water levels in Lake Powell right now, at 35, 45 feet, there's about 93,000 acres of land that previously was flooded by Lake Powell. So of those hundreds, one thing that's very unique about Glen Canyon in this region is while it's in the desert and it doesn't rain and snow a lot of these tributaries, a lot of these drainages have flowing water, either all of the year or for most of the year. That's because there's a lot of springs that come out into these drainages. So of those 127 named tributaries, there's 72 that have flowing water for the majority of the year. And if you add in a few more unnamed tributaries that also have flowing water, you got a total of 87 tributaries with water that were partially flooded by Lake Powell. And I'm walking you through this exercise because I want you to understand the scale of the landscape that was flooded by Lake Powell and has now emerged from the waters of Lake Powell. So when Lake Powell was full, a total of 600 miles of riparian ecosystems were flooded. And I'm defining this riparian ecosystem by these tributaries that have flowing water for some or all of the year. And that's not an insignificant amount of riparian ecosystems. It amounts to about 4% of the total riparian ecosystems in the state of Utah. When the lake is at about the lowest level it reached in 2023, approximately 215 miles of riparian landscapes are exposed. And most of those miles of riparian landscapes are not in those river systems, but they're in those smaller tributaries that feed the Colorado River. In fact, there's probably only about of those 215 miles, probably only 45 of those miles are on the major rivers. So I just want to, I'm going to use lots of pictures to talk about ecological succession, but I just want to just give a brief outline of the work that I've been doing in the Glen Canyon region. And I also want to just make sure we're on the same page. When I talk about Glen Canyon, Glen Canyon is the canyon that was flooded by Lake Powell. There are some portions of the region outside of Glen Canyon that were also flooded, but this study primarily focuses on Glen Canyon, which is most of the Colorado River that was flooded by Lake Powell. So I've been working on a 4-year study asking really some kind of basic questions about these landscapes, what plants and ecosystems are establishing on these emerging landscapes, and how do these ecosystems change over time? The first 2 years of this study, I established research sites. And in the second 2 years of the study, I went back and re-surveyed these sites to understand how these landscapes are changing over time. And in the study, I established a total of 88 plant surveys, sites in 21 different locations. All of these green dots represent those locations where there's 3 to 5 sites at each location. But now the focus of this study was really working in these riparian ecosystems. So ecosystems that are forming along tributaries with flowing water some or all of the year. However, I did have some sites in some of the drying bay locations as well, because on a land surface area, most of the land, the majority of the acreage of land that's now exposed is in these drying bay locations. However, as an ecologist, like thinking about the ecology of this landscape, the most diversity and richness of life is happening along these tributaries where there is flowing water. So I've kind of set the stage and given you an idea of the scope and scale of the landscape that has emerged from the waters of Lake Powell. But what happens to this landscape? Well, this is an image from, I think 2022 in a spot this area has been out of water probably for about a week or so. This is, I'm only a couple 100 feet away from Lake Powell. Well, what happens? Well, the process of ecological succession happens. And what ecological succession it is the process in which plants and animals colonize a recently disturbed landscape. And this absolutely classifies as a recently disturbed landscape. Not only was it underwater, but a tremendous amount. You see that the area along the creek here is totally dead flat. Creeks aren't usually like that. Well, it's like this because in the desert rivers and small tributaries going into the Colorado, they carry a tremendous amount of sediment with them. So aside from just the fact that the landscape was flooded and that kills all the plants and either kills or causes the animals to move out of those areas, the biggest change that happened from the flooding is the deposition of massive amounts of sediment. That the deposits of sediment range from tens of feet to a couple hundred feet. In these tributaries, it's not usually on the scale of hundreds of feet. It usually varies between 10 and probably about 60 feet. But in areas along the main stem of the Colorado, where the reservoir was for a long period of time, where a common area where the reservoir was fluctuating up and down, there's sediment deposits that are about 200 feet deep. So this newly exposed landscape, it changes rapidly. These are some repeat photographs of the same location in a place called Iceberg Canyon, 2 years apart. And the biggest change that you're seeing here has to do with this sediment. When it first emerged from the landscape, this was the picture on the left, had been out of water for about 3 years, but there hadn't been a tremendous amount of flooding that had come through. However, 2 years later, there were some very active flash flooding, kind of monsoonal rains that were occurring in southern Utah, and a tremendous amount of that sediment was moved out of the stream channel. And really, ecological succession in this landscape, there's kind of a balance between some physical factors like flowing water and floods moving sediment out of the system, and then plants growing. And when the plants grow, they establish roots, sink those roots deep in the ground. And as you get more and more plants, the cumulative effect of all of those roots is that it stabilizes those soils. So there's this kind of push and pull of erosion happening due to flooding and stabilization happening due to plant growth. And that's really kind of an important step in succession in these landscapes, is to have some of these big flash floods to start to form a proper stream channel. And this is a very dynamic system. And this illustrates that very well, that these landscapes just change very, very rapidly. Another example of some of these rapid changes come from these two photos. The photo with no plants in it had come out of Lake Powell about a month prior. The other photo that's completely full of plants was taken only 11 months later. Well, this is a case where actually a lot of invasive and non-native plants had initially established. The grass there is about a 5 foot tall grass from Asia. And if you look in the background here, these green bushy shrubs, well, those are tumbleweed. That's Russian thistle, which we see commonly all around the West. But in these landscapes, it colonizes really rapidly, is a very dominant part of the ecosystem often for the first few years, but then its abundance declines over time. Well, sometimes these newly exposed landscapes, I would say this previous thing shows somewhat, from an ecological perspective, it's somewhat of a negative change at least temporarily, in the sense that these are all non-native plants. These are plants that don't naturally grow in this landscape. We really want to see more native plants grow to create a healthy ecosystem. But here's an example where from 3 to 5 years, you have the landscape changing from one with really kind of just scattered plants, mostly non-native invasive plants, to 2 years later, you have the beginning of a thriving native riparian desert ecosystem. And one thing that is important in this change is the change happened so quickly because I'm standing on top of a beaver dam right here. So this pool of water here is actually a beaver pond. And beavers appear to speed up this process of succession. They don't necessarily change the sort of direction of it, but it makes it happen a bit faster. And that really has to do with the fact that beavers are engineers. They build dams. And what do dams do? Well, they store water. And storing that water in the landscape means that there's more water for plants to grow for a longer period of time throughout the year. Now, another place where there were some very unique and interesting rapid changes is in a place off the Escalante River. And there was an old meander of the Escalante River that was abandoned near the mouth of a place called Explorer Canyon. And as the lake came down, it left this like perched lake stuck in the meander. And then any of the water coming out of that canyon there, it couldn't make it to the river. It just kind of filled this perched lake. When I was there in 2023, there was a lake at the, a very shallow lake at the mouth of Explorer Canyon. But when I returned 2 years later, there was essentially a riparian shrubland formed and wetland grasses. And see this spot here that I'm highlighting? I'm going to show you what this looks like 2 years later in a short video. This was a lake 2 years ago. Now it is 8 foot high Salix exigua and 6 foot tall cattail. So 2 years later, this had become almost like a jungle. I mean, it was not impenetrable, but it was just wall to wall with willow and cattail, all native plants. One thing that I'm really finding is, I've shown you some of these landscapes going through some of these rapid changes in the first few years after emerging from Lake Powell. But after about 5 to 6 years, there's really kind of a step change in the kind of plants that grow there. And all of a sudden, after 5 to 7 years, you're seeing this dramatic increase in the cover of native plants. And in fact, these sites are starting to look like sites that were never flooded by Lake Powell. So there's really these rapid changes through the first 5 years. And then once you get to 5 to 7 years, you're getting a bit more stable of an ecosystem and an ecosystem that's really starting to resemble sites that were never flooded by Lake Powell. That goes along with this is some of these non-native plants that are abundant early on in succession or are abundant in the region, like tamarisk. These plants aren't doing well at all. Tamarisk, while it's very common along a lot of the rivers in the western U.S., it's kind of a very aggressive, invasive plant. These aren't doing very well at all. In general, the stands of tamarisk that exist, they established along the shores of Lake Powell when Lake Powell was high. And now as Lake Powell has dropped and those streams and rivers have cut down through the sediment, these tamarisks are now stranded 20, 30, 50 vertical feet away from a water source, and they're slowly dying. Russian thistle or tumbleweed, you can see this massive dam of tumbleweed in a creek. While it's very common in the first few years, it tends to sort of fade into the background as the landscape ages. And by the time you get to landscapes that have been out of water for 10 or 20 years, I'm really seeing thriving desert riparian ecosystems. You're seeing very important species like cottonwoods, several species of willow, other native shrub species. The level of plant species diversity on these landscapes is approaching what you'd see at sites that were never flooded by Lake Powell. In the image on the left here, you see a beaver dam, and it's no coincidence that a beaver dam helped form one of the healthiest cottonwood forests there in the background that I've seen on these emerging landscapes. The final kind of little tidbit of succession I wanted to show you is that unique and important ecosystems and components of these ecosystems are also establishing. And these are often ecosystems that are thought to be very slow to reestablish. And one of those are hanging gardens. Hanging gardens are a unique ecosystem that are really only found in the Colorado Plateau. These systems form because there's so many springs that come through this sedimentary rock. Often there'll be cracks in the canyon walls, and you'll get seeps of water coming out of the wall. And on those seeps, you get plants and mosses and algae that start to grow. And these systems are called hanging gardens. And while they aren't unique only to Glen Canyon, they are unique to the Colorado Plateau. And these systems are coming back in as little as 5 years. This is one of the healthiest hanging gardens I've seen on previously flooded landscapes, and it's only been out of water for 12 years. Another important component of desert ecosystems are biological crusts. These form on sort of loose desert soils, and they're very important to help stabilize the soils. They help retain moisture in the soil, which then helps plants grow. And they also take nitrogen from the atmosphere and bring it down into the soils. These are typically very slow growing um, communities of organisms. However, I'm seeing them established in as little as 5 years. And by the time you get to 20 years, like in this picture here, you're seeing very healthy, thick, robust biological crusts. And finally, just to summarize, the ecological changes that I've seen in Glen Canyon. Ultimately, there's rapid ecological succession that's occurring in these landscapes. Native plants tend to dominate after 5 years, including cottonwood, several species of willows, wetland grasses, wildflowers. Locations that have been exposed from Lake Powell for more than 20 years are very similar to sites that were never flooded by Lake Powell. Hanging gardens are reestablishing quickly, as are biological crusts. And it appears that the presence of beavers speeds ecological succession. In general, non-native plants are not becoming dominant in these systems. They often are in the first year or two, but then as the system ages to about 5 years, you're seeing a dramatic reduction in the cover of non-native plants. However, I would say that succession is proceeding much more slowly in these drier landscapes that are located far away from water sources. And then finally, I just wanted to mention some of the impacts of this work and how it relates to water management in the Colorado Basin. First of all, my goal in the work I do is really to create usable science, science that can be used by those managing for water and land managers. However, the future of these ecosystems will really be determined by the elevations of Lake Powell. And the future elevations of Lake Powell will be determined by future water regulation. There's some major renegotiations occurring right now of Colorado River water policy that very much impacts how Lake Powell will be managed. But regardless how that plays out, climate and drought will have a significant impact on how high or low Lake Powell is. Currently, these restoring ecosystems in Glen Canyon are not considered in water management. There's generally momentum to maintain Lake Powell at relatively high water levels due to keeping the dam running, protecting infrastructure, and also protecting, reestablishing threatened endangered fish in the Grand Canyon. And finally, I just want to say that what Glen Canyon, it has ecological value. There is value to this landscape. It is no longer a slick rock, sand-filled container for water. These restoring ecological resources, they should be considered in water management. Are they the most important issue in water management in the basin? Absolutely not. Like there's hundreds of issues that all need to be considered, but this is one that should be considered. And there are possible scenarios in which I think they're win-win scenarios in which you really don't sacrifice water and some of these ecosystems can be maintained. And I know I've run a minute or two past, but I'd be happy to answer any questions if there are any.
Seth, I love listening to you talk. It's so nostalgic. It makes me want to be back in the Southwest. We have a number of NAU alumni in attendance here,
Okay,
so
great.
a lot of Flagstaff, Colorado Plateau represented here. So fascinating to see what you're up to and the rates of succession that you're finding kind of blow my mind. Um, like Seth said, if folks want to hang out and chat with either of us, we're happy to hang out for some questions. Uh, Seth posted something in the chat there. Seth, I'll let you speak to that.
Yeah, so if any of you ever want, I know this is a little bit tangential to the lesson. However, I think that there can be some power in engaging students by showing cool pictures and, some of the effects one might not think about from Megadrought. And on both of those websites that I put out, there's the Returning Rapids project. is a bit different from what I'm doing. It's looking more at sort of sediment and how rapids are returning on some of the rivers there. But both that site and on Glen Canyon's site, not right now, but in the next week or two, there's going to be a lot of information up, including lots of pictures from the work that I've done. My whole database of repeat photography will be up and lots of other things. So there could be some resources there if you want to use that to pique students' interests.
And Seth, you said that's going up in a few weeks, you said?
Yeah, there's lots of stuff on Returning Rapids site right now.
Okay.
Glen Canyon site in the next like week, there should be a section on
Sweet.
restoring ecosystems that will appear.
Sweet. Seth, we had a
Well,
question about bugs.
yeah,
Anyone studying bugs
not
in
yet.
these canyons? Not yet. Okay.
No, yeah, no, there hasn't really been. So there is, I'm there, there's really no one else studying the ecology of these changing landscapes aside from me right now. And even prior to, the changes in the last 5 years, Glen Canyon's been a tremendously understudied place. There's very little ecological research at all, before or after the presence of the dam. So no one studied macroinvertebrates quite yet. Um, this project I was describing was really kind of like a big pilot project that's kind of been cobbled together with limited funding. I hope to, increase the amount of collaborators and, start to look at some of these issues or at least engage others to ask some of these questions because there are a lot of interesting ecological questions to ask in this landscape. But I needed to start with some basic things first.
Cool. Thanks, Seth. Yeah, anybody else got questions for Seth while we have him here? Seth, well, would it I promised without asking, would you feel comfortable sharing your slide deck with me so I can share it out with the
Yeah.
folks that have attended here this evening? Great.
Yep. Yeah, I'll just have to make a few adjustments to it and I
Yeah,
can share it as a PDF in the next day or two.
awesome. Thanks, Seth. Great. Well, if there aren't any other questions, once again, thanks so much for being here this evening. Seth, thanks to you for being here as well. These are so much more enjoyable, I think, for me and for everyone to get that perspective of what's happening on the ground and kind of the images and science behind the data sets that students are looking at. So
Yeah.
really appreciate you and your time.
Yep, you're welcome. All right. Have a good
All
evening.
right. See you,
Bye,
Seth.
everyone.
Bye, team. Thanks so much.